Welcome you all to this cryo-EM course. Last class we discussed about that signal transfer, and then we discussing about the motion correction, as well as we discussed little bit about the 2D classification. Now let's take a look in details about this 2D classification process. So in the last class I also told that okay, so what is the meaning of the 2D classification? 2D classification means that similar kind of particle we are putting it in a one particular group. When we are putting them all in one particular group, we are based on their position, we maybe have to rotate, we maybe have to translate, x and y translation is required, and then we are aligning all of them together. When we are aligning all of them together, then we are averaging out the noisy part, and only we are focusing on the signal part. Here there is one particular image, this slide I did not make it, so I collected this one. So this is a very nice slide to explain that signal enhancement by image averaging, where you can see this is the most of the noisy images, where this noisy images this is basically our signal. So now if you just look at this image, what do you have? We have the signal only. So if you just remove the noise, and then we have the noise. So now what we are doing, we are averaging out all the noisy part, and we are focusing on only the signal. So even if your protein has a some extension and which is very flexible and which is creating a noise, it may be averaged out. So here you can see we are aligning all the particles. So here this is the position we want to align all the particles. If this part is somewhere moved here, so if you think that okay, there is a another particle I have, and that particle is position is like that, if this is another signal where this particular things is rotated, if this is a circle and this triangle is somewhere here, or there is a another image or another particle. So you can see circle, and so what changes is there? Here the center is, both the cases is same, but there is a rotation of this particular thing. So if we want to align image 1 with the image 2 and the image 3, what we have to do? This particular case I have to rotate. So I have to calculate this rotation angle here. That is the important part. Also here you can see there is a change. So this particle may rotate in this way. Also it is not in the exact center, it is moved little bit up, because this boundary is touching that outside of. So here you have to move this image like that. So here you need a y translation and a rotation both. So here we are calculating all of them, then we are aligning them together, and then we are calculating the final average. So here signal to noise ratio increase proportional to root square of n. So that is one of the thing. If you have more and more particle, it will always good, it will give you the better 2D class averages. So here I will give you another very simple example that will help us to understand this entire process. So if you look at this particular image, what you can see here, I have total 8 sample, where you have a round head and large mouth. So this is the large mouth and the round head, and this is a long head, this is the elongated kind of head and the large mouth, and the other one, the mouth is very small in all the cases, and then round head and elongated head. And also there is another change it is happening, that okay, they are looking at a different direction. So this eye is looking at this direction, and this eye is looking at this direction. So there are three different changes are there. One is that large mouth and small mouth, round head and long head, and then looking at left hand side and right hand side. Now this 8 sample, I have many samples, and I use that and I froze all this sample. When we froze and we collected a cryo data, what we are getting? We are getting a very noisy images. So noisy images, first we will get the noisy image, and from these noisy images, if we consider those are our protein molecules, individual protein molecules, we have to pick it, and that I told last time, when we pull out those particles, those are called the particle picking. So from one image you will get some 10 particles, then second image you will get 8 particles, like that. So, then you will make a gallery of those particles, that is called the image stack, right. So, here you can see this is the same head, but there is a very noisy images. So, where we have a 10 copies of the 8 different types of head and a random noise are there, but here you can see those are not in same, those are mix up. So, here you can see this is the round head, large mouth, but it is shifted, it is not in same position, and this, if you just follow this, there is a mixture, there is some where it is a large mouth, there is a small mouth, all are mixed together. Sometimes the eyes are looking at this direction and some eyes are looking at this direction. So, it is a mix up. So, now what we have to do, we have to look at those particular particles and then you have to align them and you have to group them in one particular class. So, if you group them together in the next, so here if you look at this, so initially they are not aligned properly, so they are mix up, but if I just click here you can see it. So, in this particular cycle, you can see all this I arranged at as a large mouth and looking at same direction. This one is the previous one, this is mix up and this is the new one. You can see that change. So, now you can see all these particles based on their eye, based on their head size and based on their mouth size, we align them in one particular group, and then we are calculating the average from this head only and trying to remove the noise. And when we did it, we can see this is our 2D averages where signals is much better and heads are very prominent and mouth, eye position, everything is separated. This is basically the concept of this 2D classification. This is called 2D classification and this is called the 2D averages. So, this is the first step of our data processing. So, we first get our 2D averages and from there we can select only our good averages and remove the bad averages. Now, if you come here, this is our raw particle set I was discussing again and again. So, when we have this raw particle set, if we go to the next one, so this is our raw particle set and you can see it most of the time those contrasts are not that great because it is always adding some noise. Now, we are trying to focus, these are our individual protein molecules, right, and now they have a different orientation angle. So, we want to calculate that x and y translation and the rotational angle, and then we want to calculate a 2D averages of all of these particles. So, first when you will take those, we have to align them, and as I mentioned that we have to calculate that cross correlation value. When we are first aligning our particle, so we are aligning our particle based on the overall architecture of that molecule. So, in this particular case, how we can align, if you just consider in one particular room there are hundreds of students are sitting there, and now someone told you to segregate them and there is not too much reference, only thing is that you have to segregate and form a small cluster. First thing, how do you form the cluster? So, there is a two way to do it. First, overall architecture means that you can make it like that. So, height, whoever is the very long height will segregate that, okay, above 5.5 it will be a one group, in between 5.5 and 5 there is a second group, below 5 point is the another group. So, when we are trying to make this cluster, we are just taking a vague details that, okay, the height is one of the part we will consider. Same thing that, okay, if someone is bulky, that will make a group. So, based on the weight and body weight and overall shape of the body will make the another cluster. So, whoever is above 80 there is a one group, in between 70 to 80 is the another cluster, and then 60 to another cluster. So, now you can see we are implementing two parameters and overall surface or architecture we are clustering the student. So, exactly same thing here also. Initially when we will try to align our particle, we will try to align our particle based on our low frequency signal, not the very high frequency signal. When we are clustering all the students, we are not looking at, okay, I want to segregate the class like that who has the optics or their hairstyle or their, those are the fine details. So I am not paying to attention to that fine details. Initially I am paying attention to overall architecture and trying to segregate them. So they are tall, above 6 feet, and in between 5.5 to 6 feet or 5 to 5.5 feet, and then we are segregating them. Then also that overall body weight wise we are trying to segregate. So those are basically low frequency signal. If you recall what is low frequency signal, so when the signal is transferred, this is our low frequency signal. So based on this low frequency signal we are trying to segregate this particular data set at the beginning. Then we will attempt to that high frequency signal when our particles are almost aligned, and then we will think about that. So if we come to first iteration, we are trying to segregate our last slide's particle. So as I mentioned that low frequency signal, initially it will try to align and everything you will get that this kind of spherical ball. So at low frequency everything looking like a globular shape, there is nothing too much you can do. And then this is iteration 2. So if you just look at the difference between these two particles, if you just pay attention, this is iteration 1. If you go to that iteration 1 to iteration 2, you can see there are some changes in inside, some changes inside here, here also. Here also this particle shape is changing, it is looking little bit elongated. Now we are going to the another iteration. Now if you look at here, you can see some details changes in those particles, where we can see some hole inside, that is the black density, and then overall shape of this molecule is changing, and changes is happening all over, changes is happening all over. So initially when it will do the first clustering, it will do the first clustering based on that low frequency, even second iteration, third iteration, but gradually it will try to align particle in a much better way when there is a little bit extra features are there. So when we have some extra details here or extra marking, that will help to segregate only those kinds of particle. It is something like that, okay, there is a, I make a group that is 5 to 5.5 feet, okay, and then 5.5 feet to 6 feet. Now I do not want to, so if we just make this kind of group, this group maybe we have almost 100 students, but I do not want to make that big group. So then I want to make segregation like that, okay, from this particular group whoever scored above 90, I want to make a small group, then in between 80 to 90 the second group. Or if you just consider that, okay, overall looking wise I want to do, whoever has glass I will make another group, whoever without glass, whoever has a can play cricket, I will make another group. Exactly same thing, based on now I am putting more and more parameters to make a small group. Exactly same thing we are implementing here also, that we are applying all these details and which is help us to align the particles in a much better way. So same thing, we are gradually going more and more iteration, and it is helping us to segregate this data properly, and we can see the overall shape. From this one we can tell that it is a rectangular shape particle, so those shapes it is clearly visible, and from there whatever is the best 2D averages we can select it. That will be much more clear in the next slide when we will go to that one. So next let us take a look in a cryo data. So this is one cryo data we processed in our laboratory and that I am showing here. This is a 2D classification of the cryo data and this is the first iteration. If you recall clearly, that was the part you can see, this is the low frequency signal and all are looking like a globular shape, there is nothing new here. Now if we go to iteration 2 only, you can see there is a drastic change between iteration 1 and iteration 2. There are shapes are changing. Now in some cases you can see there is a rectangular shape, some molecules are coming. So those are looking different than rest of the part. There are some we cannot see anything here. So definitely when we pull out those particles, most of the time we do the automated picking, because if there is a 10 lakhs, 20 lakhs, 15 lakhs, 50 lakhs particle you want to pull out, you cannot do it by hand. So there is a algorithm, that algorithm will work and then they will pull out particle. Lot of time it will just based on that cross correlation value, it will pull out all this particle. If there is a mismatch between that cross correlation value, it will pull out lot of bad particles also. So here you can see it pull out something which is not visible anything. It may be our particle, but it is not as clean like this one or this one. So here you can see after 2D classification we can tell it pull out lot of bad particles. So from here we can select all these classes, those class, this class, this class, this and this, and delete all of this, delete all the particles what we have in these classes, what we have in these classes, particularly in those classes also. Now what we can do here, that we can try, this blue one is a good one, this blue one is a good one. So those good particle we can select here, where we can see some details and select those particle for the next round 2D classification. So here you can see this is basically the third round. If we just continue iterate, what will happen? So here you can see when we have a good particle, the alignment will be better in the next round. You can see lots of details. So here the main point is that those are the very bad particles or some kind of ice contamination. So we have to remove those part, and only that good particle whatever we have, we are just focusing on that. And if you just look at that after 15 iteration, 5th iteration, so if you look at this particular class from iteration 3rd, and if you go to iteration 5th, you can see in this class you can see more details here, more details you can see it. So here we will select only these good classes and go for the next round 3D classification. But before that, first we want to finish that iteration to until 25 or 20 iteration. So it is only 5th iteration. Now I will gradually increase that iteration. So you can see now it is a 10th iteration, and those are my good classes that I am considering, and you can see there is a lots of details you can see it. Then the 3rd iteration or 5th iteration. Now if you go 20 iteration, and finally from the 20 iteration we will select those are my good classes, and that I can consider for next round data processing or 3D classification. So 2D classification is a very good method to segregate your particle without any reference. That is why it is called the reference free 2D classification. If there is a reference, you will get the first reference and it will start aligning. There is no reference, that is the reason in the first class you can see only a globular shape, circular density, and that is why it is called a 2D reference free 2D classification. When we are getting a 2D averages, from that 2D averages if you see all the details here and perfect shape, that means whatever cryo freezing we did, that sample is good, we have a good contrast and molecule is stable, that we can use it for 3D classification. And we can also clean our data set because we used this method and we are getting those junk particles. So if you just consider, now we started with a 10 lakhs particle. If you have a 10 lakhs particle and you are classifying them, so now if you remove those things, remove those all this bad where we cannot see anything properly, and then what will happen, almost 5 lakhs bad particle you pulled out. Now whatever this red box, you have only 5 lakhs, so that you have a 5 lakhs good particle. That good particle set you are taking it for 3D classification, not the entire data set, and that is also computationally easier because initially you started with a 50 lakhs particle and this is how you cleaned your data and you end up with a small data set and then using that small data set for your 3D classification. So, this is all about the 2D classification. Definitely there are more stuffs are there that we should discuss, but not today. We will go to 3D classification part. As I mentioned that first we want to finish that 2D classification and next step will be our 3D classification. So, first let us go through that entire protocol one more time and that will help us. So, what is that workflow basically, refinement workflow if we just consider. So, this is our refinement workflow. So, first thing we have a sample and you consider this is a cryo sample. When we have the cryo sample, we take this cryo sample and we put it in a microscope and we collected a data. This is our cryo data. In this cryo data, what we have to first pay attention, there will be a power spectrum. So, power spectrum, we have a center, there is a white circle and then there is a ring and this is called the Thorne ring, and we have to see how many Thorne rings we can see. So, if we see that Thorne ring until 4 angstrom or 5 angstrom we can, or 3 angstrom we can consider that is a very good image. So, definitely when we will collect data we will do the motion correction. So, motion correction we have to do, we have to look at our power spectrum and we have to consider that those images are good enough or not for high resolution reconstruction. If we have a good data set that we have a very high resolution images, we can consider those things for data processing. So, in this data processing step, what is next? As I mentioned that when we have that raw particle, we considering that raw particle. So, here you have a raw micrograph or image. Then when you have a raw image, we pulled out those particles, individual particles. If we think that those are our protein molecules, we pulled out all these raw particles and then we are making a stack all of this. So, these are called the particles. So, that I already told you that there will be a image, first image it may be the tip and then second image tip. So, all the cases will pull out the particles. So, different number of particles it will be there in individual image. So, and then we have to save them, we have to make a stack. When we have a stack, first thing first we will get a 2D averages of this stack file. So, if you come here, so in this particular case what we are getting here, we have the cryo data, here we are doing the pre-processing. What is that pre-processing means? So, those are called the pre-processings, means we have the image, we converted them and then we do the motion correction, we calculate the power spectrum, we also calculate the CTF estimate, we will do it, that contrast transfer function estimate we will do it. From there we will get the defocus value and CS value that we are going to apply when you will do the data processing. So, those all the things are called the pre-processing, and then you have the particle stack, and when we have the particle stack, this particle stack will part of this one. Now, we will start aligning those particles that we already discussed about the 2D classification. So, when you do the alignment, what is required? We need that rotational angle and translation, x and y translation, and after the alignment we will get the first 2D classification or first 2D class averages you can consider. So, here this is my first 2D averages. While in this first 2D averages I have some good particles, those are good particles because I can see that rectangular shape, and those are my bad particles. So, I removed all the bad particles. Okay, and then we go through this cycle couple of round. So, here you can see one arrow is here. So, that means we are doing this 2D classification, we clean this data set and we go back again through this alignment. So, couple of rounds we have to do this 2D classification, sometime 3 rounds, 4 rounds or 5 rounds. When we will do that, finally we will get a very nice So, here I will erase this one, it will help us to understand that okay. So, here if you do this couple of rounds that okay. So, we are starting from first round, then second, third or fourth or fifth round, we are getting a very nice 2D averages, and you cannot see any bad particles there. Most of the 2D averages are looking good, and here you can reduce the overall particle number. When you have all this, you have some information, that x and y translation information, you have rotational angle information, and now you can generate a initial model from here, initial model from these 2D averages. So, whatever raw particle inside these 2D averages, you are taking those raw particles or you are taking those averages and you are calculating an initial model, and that is called the ab initio model. You use this ab initio model, you assign the angles here, because all this angle value you know when you align them from this 2D, you have the x and y translation, you have the rotational angle. So, now use this angle and align this initial model with all these raw particles and perform a 3D reconstruction. When you have the first 3D reconstruction, you generate a 2D projection of this 3D reconstruction. So, from that 2D projection of this 3D reconstruction, again do the angle assignment, because now you have the raw particle set here and you have the projection from the 3D object, and then it will help you to align your particle properly, and you go through this cycle couple of rounds. When your alignment everything is done, finally you will converge and get a high resolution structure, that is called the 3D reconstruction. So, this is the entire pipeline to determine the 3-dimensional structure. So, at this moment this is the process we have to follow. If we just go to the next slide, you can see it. First we are getting, so here I am just focusing on this initial model and angle assignment step. In the next slide, what we have, this slide is taken from Professor Steve Lutke's Eman tutorial. So, here I forgot to put that reference here. So, that is that Eman tutorial, he explained this entire thing. So, first what we are doing, this is initial 3D model. From this initial 3D model, we will take the 2D projection, and then 2D projection we have a raw particle here, we raw particle with align with this 2D projection from the 3D object, and then multiple reference alignment we will do. Other component we can also consider, that we can discuss in the later stage when you will do the only data processing codes, and we classify them again and calculate the average. And in this particular case, we will follow the common line method and projection matching method and get a new 3D structure. When we will get a new 3D structure, we get a 2D projection again, and again we will use this particle to align with this new 2D projection from this 3D structure, and we will go through this cycle multiple times until the model is completely converged, and finally we will get the 3D structure. Next class we will talk about the 3D structure determination, and as well as we will discuss about that resolution calculation, and then we will complete that course. Thank you all for your attention.